All right, now we're going to look at the area problem. So for a given interval, we want to be able to estimate the area under the curve, provided that the height of the curve is known at certain locations. All right, so how do we do this? We have a function, we know the function values at some certain spots, and we want to estimate then the area under the curve. Well, we have the first part here is we have an interval that we're talking about. So again, we're talking about an interval from A to B. In general, an interval from A to B. And what we're going to do is we're going to take that interval from A to B, and we're going to slice it up. We're going to split it up into many subintervals, smaller subintervals. So we're going to slice this thing up, just like we did with distance. And a lot of times we make these all equally spaced. We have just an example here of a subinterval. And conceivably with a curve, our curve is going to have, it's going to have different heights as we go along the curve. But what we're going to do is we're going to split this interval up so finely that these intervals are going to be these subintervals are going to be so short that we're going to assume the height is constant on each of the subintervals. And if we have a constant height, well, then we can figure out the area under that little section of the curve. And that's because what it would be is if we have a constant height, that means rectangle. And so what we're going to have is above each of these smaller subintervals is going to sit a little rectangle. And we can figure out the area of a rectangle. So there's the width and there's the height of our little rectangle. And area for rectangle is just height times width. So we have this whole interval that we're interested in from A to B. We're going to slice it up really finely into a whole bunch of smaller subintervals. And those subintervals are going to be so small that we're going to assume that our curve has a constant height on each of those individual subintervals. That gives us a rectangle, and we know how to do the area of a rectangle. It's just width times height. And so effectively what we're going to have then is for each of these subintervals, we're going to have the area under the curve for that little sliver of our region. So we'll get the area for this first subinterval, then we'll get the area for this next section, and then we'll just kind of repeat this. We'll get each of these individual area calculations, and we're going to call these approximating rectangles. So we're going to effectively turn our curve, or turn the region under the curve, into a whole bunch of these tiny small rectangles. And then to get the total area, we're just going to add them all together. And it's going to be a big sum. Big sum. So it's the area of all these approximating rectangles. And we're going to try this out in an example. So it always helps to work with an example here. So let's go to this one right now. We're given, and actually we have a curve. So here's our function f of x. The curve is graphed here. And a few points on this curve are plotted. So when x is 2, we know the height of the curve is 1.6, or the function value is 1.6. When our x value is 4, the function value is 0.2. And then when x is 6, the function value is 2.5. All right, so what we're seeing here is we have the graph of y equal to f of x. That's plotted for us. But then we're also given a few approximating rectangles. So essentially what we're trying to do is we want the area under this curve on the interval from 1 to 7. And what we can see here is that on this interval from 1 to 7, what we've done is we've split it up into 3 different sections. So we've sliced it up. So we have this first rectangle that goes from 1 to 3. Then we have a second rectangle here, kind of short, but it goes from 3 to 5. And then we have our third rectangle, which goes from 5 to 7. And so each of these individual rectangles here we call an approximating rectangle. And so let's think of our interval from 1 to 7. What we're doing is we're slicing this up into 3 smaller pieces. Now normally if we were going to do this for real, we would use really very short or very small subintervals here. So we'd have a whole bunch of approximating rectangles. But as our first example, and so the calculations aren't too bad, we're just using 3 here. So we have our interval from 1 to 7. And we've sliced it up into these smaller subintervals. So let's look at this first one, this first subinterval from 1 to 3. Let's get the area for that first rectangle. All right, so what's the area for rectangle? Well, it's just height times width. So we need to know, well, what is the height of this first rectangle? And we can see the height is given by the value of our function. So you can think of this as the y-coordinate. But another way to think of it is this is the function value. So this is function value f of 2. That's really how we read a graph. The x value is here, and then the corresponding f of x value goes here. That's the y-coordinate. Or we could think of it also as just being the height. That's really what a function is. It's just telling you, well, how far are you up vertically? So in this case, we're 1.6 units above the horizontal axis, above the x-axis. So there's some different interpretations here. It's the y-coordinate for this point, but since it's on a curve for our function, we can also think of it as our function value, f of 2. And then another way to think of function values is it's just the height above the x-axis. So if we wanted the area for this first rectangle, we have this one point that's giving us, or we have this, we have the height value right here. So our height is going to be 1.6. And then what's the width? We need to figure out what the width is then. Well, that's where we look at the kind of the width of our subinterval. So our first subinterval goes from 1 to 3. What's the width of that subinterval? Well, it's 2. So we get 1.6 times 2 as this area. And if we do that, it's 3.2. All right, so that's the area for that first rectangle. And then we just repeat it. We repeat it for the area of our second rectangle, and so on. So the area for our second rectangle, now we're from 3 to 5. So we have our first, now we have our second. We're going from 3 to 5. So the width is still 2. These are all nice equally spaced subintervals. So the widths are all the same. And this is where we go to our function and we look up the value here. So the height is 0.2. So we get 0.2 times 2, which is 0.4. So the area for that second rectangle is 0.4. And then we just repeat this for the third rectangle. And so the way to get the total area is we're just going to take the area for that first rectangle plus the area for our second rectangle plus the area for our third rectangle and just add them all together. And for purposes of kind of cleaning up the notation a little bit, when we say the height, which is what we're saying here, and when we're saying the width here we can think of as delta x. So a lot of times we use delta x to indicate the width. And because we're keeping these all equally spaced, all these subintervals are nice, equally spaced, delta x isn't going to change. So it's all the same width. And for our height here, if we wanted to write this using function notation, we could write this as f of 4. So this is the value, our function value at x equals 4. So x is 4, our function value is 0.2. Just like f of 2, the function value was 1.6. So really what we're doing here to get the total area is we're taking our function value, for the first rectangle, we're taking our function value at 2 times delta x. Then for our second rectangle, we're taking our function value reading at 4, so f of 4, then times delta x. And then for our third rectangle, this is where we're taking the x value is 6. So this will be f of 6 times delta x. And if we do all these calculations, what do we get? We get 1.6 times 2 plus 0.2 times 2 plus 2.5 times 2. And if we add all that up, we end up with 8.6. So there's an estimate. There's an approximation for the total area under the curve. So in this one we did 3 subintervals. And then we found the area for each of the corresponding rectangles, added those areas together to give us the total area. All right, so we're seeing here, if we look at our total area calculation here, it should feel kind of similar to the distance calculation that we did in the last example. So we're going to kind of we're going to explore that similarity next.